At the end of this chapter, you'll be able to identify and locate the components of the power plant, describe the layout of the power plant and identify its subsystems and interface, identify and locate the components of the engine, describe the layout of the engine and identify its subsystems and interface, explain the operation of the engine main components, identify and explain the controls associated with the engine, identify and explain the indications and annunciators associated with the engine, identify and locate the components of the propeller system, describe the layout of the propeller system and identify its subsystems and interface, explain the operation of the propeller system main components, identify and explain the controls associated with the propeller system, identify and explain the indications and annunciators associated with the propeller system, identify and locate the components of the engine control system, explain the operation of the engine control system main components, identify and explain the controls associated with the engine control system, identify and explain the indications and annunciators associated with the engine control system. Provide the correct answers to the questions in this chapter. The ATR72-500 aircraft is powered by two power plants, each containing a turboprop Pratt & Whitney 127F or 127M engine, driving a Hamilton standard variable pitch propeller through a reduction gearbox. The PW127 engine has, in normal operation, a takeoff power of 2,475 shaft horsepower, with a reserve takeoff power of 2,750 shp in case one engine fails. Each engine incorporates an engine air intake, which is offset and has a shallow S-bend design to provide uniform inlet air to the engine compressor. The curvature in the air intake is intended to provide inertial separation and protection in the event of foreign object ingestion. It is also used to divide airflow in primary flow to the engine and a secondary flow to the oil cooler. Control of the secondary airflow is achieved by automatic oil cooler door flaps position. Examine the table Engine Parameters. You'll find important data for safe engine operation. Note that operating the engine beyond these limits may require maintenance action. Also, closely examine the graph's over-torque limits. Note that for engine operation up to 106.3% torque, the time is unlimited when the propeller speed NP is lower than 94%. Over temperature limits for starting and engine operating. The Pratt & Whitney PW127 is a turboprop engine with modular design made up of a reduction gearbox module and a turbo machinery module. The turbo machinery is a 3 concentric shaft design and houses a high-pressure centrifugal compressor driven by a single-stage high-pressure turbine, which forms the high-pressure spool. The centrifugal low-pressure compressor driven by a single-stage low-pressure turbine forms the low-pressure spool. The two-stage power turbine and drive shaft is connected to the torque shaft, which drives the reduction gearbox. The combustion system consists of an annular reverse flow combustion chamber, 14 fuel nozzles, and a dual ignition exciter system. The reduction gearbox is a twin lay-shaft design containing the first and second stage reduction gears and the offset propeller shaft. The reduction gearbox and the turbo machinery can be divided into different build groups that support the main engine bearings and shafts. The reduction gearbox consists of 3 housings: the reduction gearbox front housing, the reduction gearbox center housing, and the reduction gearbox input housing. The turbo machinery consists of the front inlet case, which connects the reduction gearbox to the turbo machinery, the rear inlet case, the low-pressure diffuser case, the intercompressor case, the gas generator case, and the turbine support case. Engine control is achieved by 2 control levers for each engine, the power lever and the condition lever. The power levers control engine power in the forward range and propeller blade angle in the idle through reverse beta range. The condition levers set propeller RPM in the forward thrust range, provide manual propeller feathering, and fuel on-off control for engine start and shutdown. This lesson provides you with an overview of the location of the engine control panels. On the main instrument panel, you'll find the Engine 1 and Engine 2 control panel, and the power management panel. On the overhead panel, you see the engine start panel. It contains the engine start and the propeller brake controls. All panels will be explained in detail in upcoming lessons. The purpose of the reduction gearbox is to reduce the power turbine input speed into a suitable output speed for propeller operation via a 2-stage reduction gear train. The reduction gearbox, RGB, consists of the front, rear, and input drive housings, which together make up a housing set, and an accessory drive cover. The reduction gearbox also provides mounting pads for components that control engine and propeller operation. The turbo machinery is the part of the engine which develops power to drive the propeller. The major sections of the turbo machinery are the inlet section, the compressor section, the combustion section, and the turbine section. To control and monitor engine power and to provide energy sources for aircraft systems, accessories are installed on the turbo machinery. The air inlet section consists of the front inlet case and the rear inlet case. The front inlet case contains the engine air intake and provides mounting points for the engine electronic control box, EEC, and the auto feathering unit, AFU, on the left side. On the right side of the front inlet case, there are mounting points for the ignition exciter box, the fuel flow transmitter, and the turbo machinery data plate. The rear inlet case provides mounting pads for the fuel pump and the hydromechanical fuel control, HMU, and the starter generator. The engine oil tank, located at the lower side of the casing, forms an integral part of the casing. The compressor section includes the 2 independent impellers, a low-pressure and a high-pressure centrifugal impeller. The low-pressure impeller is contained within the low-pressure diffuser case. and the high-pressure impeller is contained within the intercompressor case. Diffuser pipes, which also increase the air pressure, connect the diffuser case to the intercompressor case. Combustion takes place within the gas generator case and contains an annular reverse flow combustion section, which consists of a combustion outer liner and a combustion inner liner. The fuel manifold adapters mounted around the exterior of the gas generator case protrude with the spray nozzles into the combustion chamber outer liner. Two igniter plugs mounted on the gas generator case ignite the air-fuel mixture during engine start. The gas generator case incorporates an air bleed pad through which P3 air is supplied to the aircraft environmental control system. The turbines are located within the turbine support case and contain the high-pressure turbine, the low-pressure turbine, and the power turbine. The power turbines, mounted on the power turbine shaft, connect the two-stage power turbine via the torque shaft to the gearbox. The low-pressure turbine shaft connects the low-pressure turbine to the low-pressure impeller. The high-pressure turbine is connected to the high-pressure impeller by the high-pressure turbine stub shaft. The accessory gearbox is driven by a bevel gear, which is secured to the high-pressure impeller. A tower shaft bevel gear transmits the rotation from the high-pressure impeller via an angle drive gearbox to the accessory drive housing. During engine start, the starter generator transmits its rotation via the angle drive gearbox and tower shaft to the high-pressure impeller. Note that the starters are limited to 3 starts with a 1-minute 30-second maximum combined starter running time, followed by 4 minutes off time. Let's look at the basic operational principle of how this engine develops its power. Air entering at the engine inlet is directed rearward and ducted to the low-pressure compressor. From there, it is directed through external ducts to the high-pressure compressor, where it undergoes a second stage of compression. The compressed air then enters internal ducts and is discharged into the combustion chamber, where fuel is added and ignited. Gases exiting the combustion section initially impact onto a single-stage high-pressure turbine and extract energy from the flow to drive the high-pressure compressor. A gear drive attached to this compressor drives the accessory gearbox mounted on the top section of the turbo machinery. Mounted behind the high-pressure turbine is a single-stage low-pressure turbine, which also extracts gas energy to drive the low-pressure compressor. As the combustion gases continue to flow rearward, they are directed towards the two-stage power turbine assembly. The power turbines turn as a single unit, extracting the majority of gas energy remaining to rotate a shaft that is connected to the reduction gearbox. After leaving the power turbine, the gases are vented through to the exhaust pipe, where they are vented overboard. The engine fuel system consists of 2 subsystems, a fuel control system and a fuel distribution system that provides the engine with scheduled fuel for combustion. The engine fuel control system is composed of an engine electronic control box, EEC, and a hydromechanical unit, HMU. The components of the fuel distribution system include a fuel heater, also used to cool the engine oil, a low and a high pressure fuel filter, a high pressure fuel pump, a flow meter, a fuel-cooled oil cooler, FCOC, used for cooling the lubricating system by using the fuel as cooling source, a flow divider, and the fuel nozzles. In normal operation, the engine receives fuel from the fuel tank, located inside the respective wing. During engine start, fuel is delivered under pressure to the engine by means of the suction generated by the engine-driven high-pressure fuel pump, and by an electrical fuel pump installed in the fuel tank. During engine start, the fuel jet pump takes over from the electrical fuel pump 30 seconds after the high-pressure fuel pump is delivering fuel under the correct pressure, and the fuel pressure produced by the jet pump is at 8.5 psi. At this moment, the electrical fuel pump is automatically switched off. In the event the fuel pressure drops below 5 psi, the electrical pump is switched on automatically. The fuel enters the engine at the fuel heater, where the fuel is filtered and heated by the engine oil to eliminate ice crystals in the fuel. A fuel temperature sensor is installed in the fuel outlet of the fuel heater to indicate the engine fuel temperature in the cockpit display. Fuel from the fuel heater enters the high-pressure fuel pump, where the fuel pressure is increased and the fuel is filtered before flowing internally to the hydromechanical unit, or HMU. A fuel clog indicator will illuminate in the cockpit to alert the pilots if the high-pressure fuel pump filter is blocked and bypassed. The HMU will meter the fuel for the correct engine requirements and will also produce a high-pressure fuel flow to generate the motive flow. Metered fuel from the HMU passes via a flow meter, which indicates the fuel consumption in the cockpit display, to the fuel-cooled oil cooler. The FCOC cools down the lubricating oil by using the fuel as cooling source. From the FCOC, the fuel goes to the fuel flow divider mounted on the fuel inlet manifold. The fuel flow divider divides the fuel into a primary and secondary flow to the 14 fuel nozzle adapters, which are installed in the gas generator case. The engine oil system is responsible for feeding the turbo machinery, the reduction gearbox, and the propeller pitch change mechanism. It is a wet sump type with the following main components: an integral oil tank within the rear inlet case, an oil filler neck with cap for refilling of the oil system, a sight glass or dipstick to visually check the oil level within the tank, a gear pump driven by the turbo machinery gearbox, an air cooler system mounted in the engine nacelle, and an oil filter, both fitted with a bypass system. An oil cooler, fuel heater, an oil temperature sensor, a fuel-cooled oil cooler, a low-temperature valve used to avoid damaging pressure surges during cold weather starts, an oil low-pressure switch for cockpit warning, and an oil pressure transmitter for cockpit oil pressure indication. The pressure-regulating valve assembly regulates the engine oil pressure within the engine lubrication system. The main oil filter housing assembly houses the filter bypass valve and the oil filter impending bypass switch. This check valve also provides a mounting point for the oil temperature sensor, which is used for engine oil temperature indication. The oil gear pump supplies pressurized oil for the oil system. A magnetic chip detector mounted in the oil tank detects metal particles in the oil flow. The reduction gearbox lubrication system uses oil from the engine oil tank. Through a flexible oil line, the oil flows from the oil gear pump to the air oil cooler, where the oil is cooled to normal operating temperature. The oil leaves the air oil cooler by a flexible oil line and flows to the oil filter housing inlet. Oil from the oil filter housing is guided into the fuel heater to heat the fuel and eliminate possible ice crystals. From the oil to fuel heater, the oil flows through an external oil tube through the FCOC, where the oil is cooled by fuel, into the reduction gearbox integral oil tank, from where the oil is distributed to the propeller valve module pump, high pressure pump, the propeller overspeed governor, the electric feathering pump, and to the reduction gearbox internal gears and bearings. The reduction gearbox is scavenged by an oil pump mounted in the oil pack and draws the oil from the bottom of the reduction gearbox through an anti-siphon line into the front inlet case to provide the intake with anti-icing protection. Oil leaving the front inlet case flows through an external oil line into the reduction gearbox scavenge pump. Then, via the reduction filter housing where the oil is filtered, the oil is returned back into the engine oil tank. As soon as the starter generator initiates the engine start sequence, the oil gear pump will be driven via spur gears and sucks oil from the engine oil tank. The low temperature valve is installed after the oil gear pump to return oil to the tank in the event a pressure surge is sensed during cold starting. The air oil cooler bypasses the oil until above normal operating temperatures are achieved. Oil from the oil gear pump flows through the high-pressure oil filter. In case of a filter blockage, the oil will be bypassed through the filter bypass valve. From the oil filter, the oil flows in two directions: to the oil to fuel heater, FCOC, and reduction gearbox, and to the check valve housing. Before the oil enters the check valve, a part of the oil is guided to the number 1 and 2 bearing cavity, the accessory gearbox, and the angled drive gearbox for lubrication of the gears and bearings. In the check valve housing, a temperature sensor provides oil temperature indication. Oil from the tank flows by internal passages and tubes to the electric feathering pump, to the overspeed governor, and to the propeller control unit pump, also called the PCU pump. The propeller control unit receives pressurized oil from the electric feathering pump and the PCU pump, and receives a signal oil pressure from the overspeed governor to control the propeller pitch mechanism. Oil from the auxiliary tank is also distributed through internal galleries to lubricate the reduction and accessory gear trains and bearings. Here is the list of approved lubricating oils. Note that ATR doesn't recommend mixing of different brands or viscosities. The ignition systems, one for each engine, consist of one ignition exciter and 2 spark igniters joined by electrical cables. The ignition exciter of each engine is supplied by the DC essential bus and is controlled from the cockpit by the engine start rotary selector to provide ignition during the start cycle. The power lever system is used to initiate fuel demands to drive the engine in the forward operating range, and controls the propeller blade angle from ground idle to full reverse. The condition lever controls the propeller speed, in P in flight, controls the propeller feather selection, and the fuel during engine start and engine shutoff. The power levers and condition levers are mounted in the center pedestal and are connected to the respective engine by means of push rods, cables, pulleys, and push-pull cables. The power lever push-pull cable is connected to the fuel hydromechanical control unit lever and to the propeller valve module PVM via pushrods. The condition lever push-pull cable is connected to the PVM and via pushrods to the HMU for the fuel cutoff function. If the power lever is moved, its movement is relayed to the associated lever on the HMU. The angular movements of the HMU lever arms are referred to as power lever angle, PLA, and are measured in degrees. The engine and propeller assembly generates power or propulsion required for the aircraft operation. It is achieved through the power lever of the respective engine and is indicated to the flight crew in terms of torque. The torque is obtained by dividing the engine power, P, by the propeller speed, NP. The engine power is controlled by the power lever that controls the fuel flow, which governs the high-pressure compressor speed, NH. NP is controlled either by the power lever or by the condition lever, depending on the control mode, which will be explained later in this chapter. The NP is normally maintained at a constant, predetermined value by the adjustment of the blade's angle. In order to precisely deliver the fuel demanded by the engine, one engine electronic control, EEC, is installed on each engine. The engine electronic control, among other functions, controls the fuel flow in the respective HMU through a stepper motor, which lowers the fuel flow ordered by the HMU. The engine electronic control considers the outside conditions and the positions of the power lever, power management selector, and bleed valves. The EEC is selectable by means of a push button. In the event of an engine electronic control failure, the HMU alone controls the engine fuel schedule. The engine governing system main components are the hydromechanical unit, HMU, the engine electronic control, EEC, the propeller valve module, PVM, and the power management selector. The HMU performs the fuel metering in steady-state operation and also protects the system in case of transients. Moreover, it commands the high-pressure compressor speed, NH, according to two different laws, depending on the EEC selection. The HMU also provides the fuel shutoff function, controlled by the condition lever, and provides the motive flow to the fuel tank jet pump. The engine electronic control, via the HMU stepper motor, regulates the fuel flow to obtain the desired torque and protects the engine against NH overspeed. It also ensures a minimum propeller speed on ground at low power settings, and controls the modulated opening of the handling bleed valve, HBV, ensuring the correct low-pressure compressor operation. In case of an engine failure during takeoff, the EEC also delivers the automatic up-trimmed takeoff power to the operative engine. This function will be explained later. The PVM controls, at high power settings, the propeller maximum speed, NP, according to the power management selector selection. Further, it controls the propeller pitch at low power settings and when using reverse, thus ensuring low pitch when the respective power lever is below the flight idle position. The power management selector provides the EEC and the propeller control system with the power and NP requirements corresponding to the selected position. The engine power control top law is used when the EEC is on and operative. With the power lever set on the white mark, notch position, and according to the selected position on the power management, the engine electronic control automatically sets the maximum engine power and torque for a given propeller speed in all ambient conditions. The engine power control base law is used when the EEC is manually deselected. In this case, the engine power is given in function of the power lever position. This mode of operation is also called reversion mode and is characterized by loss of the torque regulation at a constant power lever position. Any change in the ambient conditions will require adjusting the power lever in order to maintain the maximum available engine torque. And loss of propeller under speed control on ground at low power setting. Note that the loss of the EEC will not affect the torque indications displayed, both digital and analogic, and that the HBV is still monitored by the deselected EEC, thus ensuring the correct low-pressure compressor operation. The maximum engine power setting in the top law, or engine regulation, uses pitot and static data coming from the engine electronic control. The EEC data in normal operation comes from the selected ADC on the ADC switch. In case both ADCs fail, engine sensors will feed the EECs with less accurate information. If the selected ADC electrical supply fails, two possibilities may occur. In case ADC 2 was selected, ADC 1 immediately takes over. In this case, the CCAS is activated and the master caution flashes amber. A single chime is generated. The amber engine light illuminates on the CAP, and the amber ADC switch fault light illuminates. In case ADC 1 was selected, the engine sensors immediately take over, and the ADC switch fault light does not illuminate. Each power lever has selectable settings identified as forward stop, go-around ramp, max rated torque, notch, white marks, flight idle, the minimum in-flight power setting, ground idle, and maximum reverse. The idle gate is a protection for the power levers that prevents the movement of the levers towards ground idle and max reverse in flight. A gust lock system is installed forward of the power levers. Once the gust lock lever is engaged, it's not possible to advance either power lever further than slightly above flight idle position in order to prevent a takeoff with the flight controls locked and a high power setting when in hotel mode. For takeoff, the power levers shall be manually advanced above the flight idle position and placed in the notch position, indicated by a white band. The power lever's position beyond the notch is characterized by a ramp threshold and is used for go-around. It may also be used in case of an engine failure at takeoff, followed by an ATPCS failure. In this position, the power delivered is the maximum go-around power or reserve takeoff power, irrespective of the power management position. The ramp threshold may be overridden up to the most forward position only in case of an emergency. This situation provides up to 15% more power than the reserve takeoff power. After landing, to reduce the power levers from flight idle to ground idle, first the idle gate has to automatically unlock, and then the pilot has to act on power lever triggers. Any position of the power levers below flight idle must be used on ground only. A spring rod protects max reverse, so that a force must be exercised to position the power lever in the reverse sector. Releasing the force will bring the power lever back to around ground idle. Observe that in case of an engine failure, the power lever continues to control the propeller blade's pitch angle and as a result, the propeller drag, as long as the respective propeller is not feathered. Each control lever has 4 distinct settings: fuel shutoff, propeller feather, auto, and 100% override. The positions auto and 100% override are noticed by a notch. In the auto position, the propeller speed is controlled through the power management selector positions, and in the 100% override position, the propeller is manually set to max RPM 100% of NP. To select the condition lever from auto to feather, and from feather to fuel shutoff, it's necessary to act on the condition lever's triggers. A red light on top of each condition lever will illuminate in case a fire is detected on the associated engine, provided the condition lever is not in the fuel shutoff position. The flight idle gate prevents the power levers from being retarded below the flight idle position as soon as the landing gear shock absorbers are released. At landing, as soon as the shock absorbers are compressed, this gate automatically unlocks and the power levers can be moved down to ground idle and reverse. The idle gate fail light illuminates amber, and the CCAS is activated when the gate does not engage automatically in flight or does not unlock automatically after landing. In this case, the master caution flashing light is activated together with a single chime, and the amber idle gate light on the CAP and the amber idle gate fail light on the pedestal are also illuminated. Whenever this occurs, a manual override is possible by pushing the idle gate lever in flight or by pulling the idle gate on ground. On ground, an amber band becomes visible on the idle gate lever when it is pulled. The Engine 1 and Engine 2 control panel contains 3 push buttons and 4 indications. The engine electronic control push buttons, one for each engine, are named EEC1 and EEC2. They can be manually switched on or off and are fitted with an integrated fault light that's in normal conditions not illuminated. When the push button is pressed, the EEC is selected on and adjusts all HMU actions via the stepper motor. If the push button is released, the EEC is selected off and the HMU directly controls the rotation speed of the high-pressure spool as a function of the PL angle. In this case, the white off light illuminates. Note that if a failure in the EEC is detected, the CCAS activates the flashing master caution amber light, the single chime, the engine amber light on the CAP, and the associated EEC fault light. It's important to observe that in case of an EEC failure, the EEC fault light initially flashes, and while the fault light is flashing, it's forbidden to deselect the associated EEC. Furthermore, if the associated power lever is set above 52 degrees PLA, the NH is automatically frozen to the value before the failure occurred, and the affected power lever becomes inefficient until being reduced below 52 degrees PLA. This is called fail-fix function. Once the power lever is reduced below 52 degrees PLA, the reversion to the HMU base law automatically occurs. The engine loses power. The engine electronic control fault light illuminates steady, and the power lever is again active in order to restore the engine power. For the correct sequence of action, consult the QRH. The low pitch and up trim indications and the ATPCS push button will be explained in detail in upcoming lessons. Located on the overhead panel, the engine start rotary selector allows the selection of the ignition exciter for the start sequence. The position off and start abort de-energizes the ignition circuit, thus interrupting or disarming a start sequence. The position crank is used to crank the engine when performing a dry motoring start. This is mostly performed following an abnormal engine start and according to the QRH. In this position, the ignition is inhibited. On ground, the engines can be started by selecting the engine start rotary selector to start A, start B, or start A and B. Note that the use of the position start A and B can hide a failure of either exciter A or exciter B. Thus, ATR recommends using start A on odd days and start B on even days, or alternatively, start A for the first leg and start B for the second leg to reveal exciter failures. If an in-flight engine start is necessary, exciters A and B are both used regardless of the engine start rotary selector position. Furthermore, if an in-flight engine malfunction happens and the NH of one engine drops below 60%, both exciters A and B are automatically activated in order to attempt an automatic engine relight. The automatic engine relight function is inhibited if the NH drops below 30%, or the engine electronic control is selected off, or the respective condition lever is set to feather or fuel shutoff, or on the failed engine after an ATPCS sequence. In case one or both EECs are selected off, the exciters A and B can be manually continuously activated for both engines together by depressing the guarded manual ignition push button. Observe that in this case the blue on light illuminates in the push button. The start push buttons, one for each engine, are located on the left and right side of the engine start rotary selector. By momentarily depressing the push button, the engine start sequence of the respective engine is initiated. The on light illuminates white until reaching 45% NH and then automatically extinguishes, indicating that the engine has reached self-sustaining speed. The buttons have an integrated fault light that will illuminate in the following situations. The engine starter remains engaged after reaching 45% NH. The associated generator control unit fails during the starting sequence. On the right-hand engine, when the propeller brake is on but the gust lock is not properly engaged. On the main instrument panel, the power management panel is installed. This panel is composed of the power management rotary selector, PEC single channel lights, and PEC fault push buttons. The power management rotary knob is composed of two independent parts used to provide the FDAU target bugs located in the torque indicators, PIU, and EEC with basic power requirements corresponding to the selected position. The front part controls the right engine, while the back part controls the left engine. There are four distinct positions: TO, takeoff, MCT, maximum continuous torque, CLB, climb, and CRZ, cruise. Note that the FDAU target bug represent the maximum torque available for a given power management position. In the position takeoff, the FDAU target bug indicate the reserve takeoff torque. Therefore, the pilots need to determine the takeoff torque from the associated performance table. The PEC single channel light illuminates amber in case one channel of the referred PEC is lost. In this situation, no other visual or aural indication is generated, and the system automatically transfers the PEC control to the backup channel. On ground, every time the propeller is unfeathered, the low-pitch protection is tested by the PEC. The backup channel is used during 2 seconds, causing the single-channel light to illuminate while the propeller is unfeathered, then it extinguishes. This indicates the correct working of the PEC backup channel. The PEC fault push button is in its normal operation, depressed and dark. In case both PEC channels are lost, the amber fault light illuminates in the respective push button, the master caution flashes amber, a single chime is generated, and the amber engine light illuminates on the CAP. By releasing the push button, the respective PEC is deactivated. The propeller speed is blocked at 102% and the white off light illuminates. Note that in case of a PEC fault, reverse is not available on the affected engine, and the minimum propeller speed on ground is no longer assured by the system. Therefore, the associated ACW generator may be lost if the propeller speed drops below 65.5% on the affected engine. In this lesson, you'll perform the Engine 1 start. Before starting any engine, the EEC fault light must be extinguished. In case the EEC fault light is illuminated, a reset should be tried. If unsuccessful, deselect the affected engine electronic control. Let's assume that your aircraft is in hotel mode, ready for startup and everything is prepared correctly. Select the Engine Start rotary selector to position Start A. Depress the Start push button, check the on light, and watch NH coming up. When passing 10% NH, move the condition lever from position Fuel Shutoff to position Feather. At 45% NH, check to see that the Start push button on light automatically extinguishes. When passing 65% NH, check that the DC generator 1 fault light automatically extinguishes. Observe the engine parameters stabilized at idle values. NH equals 67%, ITT equals 580 degrees Celsius, FF equals 110 kilograms per hour. Select Engine Start rotary selector to position Off and Start Abort, and set the respective condition lever to Auto. Good, you've successfully started the engine. Note, passing from fuel shutoff to feather position is possible between 10% and 19% NH if internal turbine temperature is above 200 degrees Celsius. The engine shall light up within 10 seconds after setting the condition lever to the position feather. Carefully monitor the engine start limitation during the start sequence. If one limit is exceeded, immediately apply the corresponding memory items described in the QRH procedures following failures, abnormal parameters during engine start, and then follow the applicable checklist.
The aircraft is equipped with 2 variable pitch Hamilton standard propeller assemblies, mounted with nuts to the reduction gearbox propeller shaft. Each propeller system consists of a Hamilton standard 568F 6-blade right-hand rotation propeller with a diameter of 3.93 meters. A propeller valve module, PVM, a propeller electronic control, PEC, an overspeed governor, a high-pressure hydraulic pump, an electrical feathering pump, a propeller synchrophaser system, and a power management selector switch. Each of the propeller assemblies consists of 6 blades with external deicers and counterweights, the propeller hub assembly, blade retention hardware, a pitch change actuator, a spinner and bulkhead, and an oil transfer tube. The propeller pitch regulation system maintains the selected propeller speed. This is done by electrical and hydromechanical means. Mounted on the propeller gearbox, the propeller valve module, PVM, and the propeller electronic control, PEC, enable the propeller control according to the positions of both condition and power levers and the power management selector switch. The propeller valve module, PVM, is the main component of the blade angle and speed governing controls. The PVM receives mechanical and electrical inputs from the flight compartment and enables propeller pitch change operation. The PVM main elements are the engine power lever mechanical input, the electro-hydraulic valve, EHV, the protection valve, the electrical feather solenoid, the secondary low-pitch stop-retract solenoid, and the blade angle feedback. The flight compartment condition lever controls the PVM condition lever, while the power lever controls the PVM power lever. The condition lever input is used to activate the mechanical feathering valve when feathering is selected. The PVM condition lever is also mechanically connected to the HMU high-pressure shutoff valve lever. This allows, after propeller feathering, the closure of the high-pressure fuel shutoff valve on the respective HMU. The power lever input is used to directly provide the PEC with the selected power lever position. The electro-hydraulic valve, EHV, is a part of the propeller valve module and is commanded by the PEC via dual windings, one per PEC channel. The EHV modulates the high-pressure supply oil from the gearbox-mounted pump to increase or decrease pitch pressure. The protection valve is a hydraulically operated valve that controls the fluid flow to the propeller actuator. It is operated by hydraulic pressure supplied to both ends of the valve and can shift to port decrease pitch pressure to drain, resulting in pitch increase. The signal to it is produced by the overspeed governor, the feather solenoid, or the low-pitch stop protection. The electrical feather solenoid permits the propeller to go to the maximum course pitch, feather position. It controls a drain from the large area side of the protection valve. Operation of the solenoid opens the drain, and pressure on the large area of the protection valve decreases to the minimum. Movement of the protection valve will then cause the propeller to feather. The secondary low-pitch stop-retract solenoid operation is used to move a ball valve that permits or stops the oil supply from the overspeed governor to the transfer bearings. This allows or cancels operation of the in-flight fine pitch stop, secondary low-pitch protection. In flight, the secondary low-pitch protection is not supplied. The propeller is prevented from going below a specified fine pitch angle by the oil transfer tube in the transfer bearing. On ground, the secondary low-pitch protection is supplied with a PL, below, FI signal because the propeller must be permitted to operate in a ground range. For this reason, the secondary low-pitch protection solenoid cancels the in-flight low-pitch stop. In flight, the low-pitch light illumination indicates that the propeller pitch is lower than 8 degrees blade angle. The blade angle feedback mechanism is used to give an indication of the propeller blade angle to the PEC. The mechanism is operated by the axial movement of the oil transfer tube acting on a double RVDT, giving blade angle feedback to both primary and backup PEC channels. The PVM is supplied with oil under pressure from the auxiliary tank, which is an integral part of the propeller gearbox. This tank is pressurized, fed with oil from the engine lubrication system, and is always filled even if the engine is shut down. The oil from the tank supplies a mechanical high-pressure pump and an electrical feathering pump. A propeller electronic control is located on each engine and is a dual-channel electronic box which provides closed-loop control of the propeller pitch change system during propeller speed governing. It operates in the beta and reverse modes for feathering and unfeathering of the propeller and synchrophasing. The PEC receives the following inputs from the aircraft: 28-volt DC from normal and emergency buses, PLA position through 2 RVDTs located in the PVM, propeller speed selection 82% or 100%, feather signal from the condition lever positions, shut off and feather, emergency feather signals from ATPCS or fire handle, weight on wheel from proximity switches, blade angle position through an RVDT within the PVM, and the propeller speed from the NP sensor. The propeller electronic control provides control to the EHV within the PVM, signal to the PEC single-channel amber light in the cockpit, signal to the low-pitch amber light in the cockpit, and information for maintenance flag fault codes. The mechanical high-pressure pump is a constant flow type installed at and driven by the propeller gearbox. When feathering an operative engine propeller, the electric feathering pump provides additional oil pressure supply to the mechanical high-pressure pump in order to ensure a safe and complete operation. The electrical feathering pump is located on the forward right side of the engine and is comprised of an electrical motor driving a pump. Its operation is automatically limited to 30 seconds to prevent overheating the electrical motor. Note that the electrical feathering pump alone produces sufficient oil pressure to feather an inoperative engine propeller. The pressure output from the mechanical high-pressure pump and the electrical feathering pump is called supply pressure. The supply pressure is routed to the overspeed governor, to the PVM, and to the transfer tube. The function of the PVM is to supply oil pressure to the pitch change actuator, which results in propeller blade angle changes. The overspeed governor is installed on and driven by the propeller reduction gearbox. It's composed of a hydraulic section and a pneumatic section. In case an overspeed is detected, the hydraulic section initially reduces the supply pressure. The pneumatic section is an additional safeguard in case the hydraulic section is not able to regulate the supply pressure. If this happens, the pneumatic section bleeds air from the engine high-pressure compressor to force the HMU to reduce the engine fuel flow. By reducing the engine fuel flow, the engine power is reduced, and by consequence, the propeller speed is reduced. In normal operation, high-pressure oil pressure from the pump is routed through the overspeed governor to the high-pressure side of the protection valve and applied to the electro-hydraulic valve, EHV. In this position, the protection valve is ready to route the metered pressure, increase or decrease, from the EHV to the pitch change actuator. If a propeller overspeed occurs at approximately 103% NP, the overspeed governor flyweights open the slide valve and drain the pressure applied to the high-pressure side of the protection valve. As a result, the protection valve shifts. This causes the protection valve to route a high pressure to the increased pitch chamber of the pitch change actuator. This results in a blade pitch increase and propeller speed decrease and is maintained at 103% NP. At landing, when the power is selected below flight idle, the speed reset solenoid energizes. This pressurizes the reset piston. When the reset piston is pressurized, it puts more force on the speeder spring, which increases the speed setting of the governor, 118% instead of 103%. This causes the governor to keep the high-pressure signal to the protection valve on a higher speed range. This prevents momentary propeller overspeed to allow full reverse operation. Now that we're familiar with the components that supply and control oil pressure to control the propeller pitch, let's see how the pitch change occurs. As a result of the pilot's input, the PEC supplies a command current to the electro-hydraulic valve, EHV, to perform the calculated pitch change rate. High pressure supply from the high-pressure pump or feathering pump, depending on the mode, will be modified into a metered pressure. The valve will route the metered pressure through the oil transfer tube either to the decrease or increase pitch change of the pitch change actuator. An increased pitch signal will cause the slide valve to route the metered pressure to the increased pitch chamber of the pitch change actuator and to connect the decreased pitch chamber to the return. As a result, the actuator moves rearward, driving the blades to increase pitch. And as the oil transfer tube is attached to and moves axially with the pitch change actuator yoke, oil transfer tube axial position is a direct indication of the propeller blade pitch. Motion of the oil transfer tube contacts the RVDTs, rotary variable differential transformers, which transmits the position of the propeller blade angle position feedback, to the PEC. When the blade angle position feedback to the PEC is in accordance with the command, operation ceases. A decreased pitch change signal will cause the slide valve to route the metered pressure to the decreased pitch chamber of the pitch change actuator and to connect the increased pitch chamber to the return. As a result, the actuator moves forward, driving the blades to decrease pitch, and as the oil transfer tube is attached to and moves axially with the pitch actuator yoke, oil transfer tube axial position is a direct indication of the propeller blade pitch. Motion of the oil transfer contacts the RVDTs, rotary variable differential transformers, which transmits to the PEC the position of the propeller blade angle position feedback. When the blade angle position feedback to the PEC is in accordance with the command, operation ceases. The propeller can be feathered manually by setting the condition lever to the feather position in normal operation or in case of an engine failure, manually by pulling the fire handle, or automatically by the ATPCS system following an engine failure. Normal feathering of the propeller is performed by a feather control signal sent from the condition lever through the PEC to the electronic hydraulic valve, EHV. When the propeller is controlled to feather, the feather solenoid is energized and the PEC provides a feathering signal to the electro-hydraulic valve, EHV. As the solenoid is energized, high pressure from the pump is drained. As a result, the protection valve shifts and routes the high pressure to the increased pitch chamber of the pitch change actuator. Once in feather position, the propeller is set and locked at 78.5 degree blade angle. When the condition lever is moved out of feather, the feather solenoid is de-energized, blanking off the drain, and the PEC begins the unfeathering sequence. This routes the hydraulic pressure from the high-pressure pump to the decrease side of the pitch change actuator. During unfeathering, the PEC will limit the decreased pitch rate until propeller RPM is near the selected governing RPM. Note, during unfeathering, low pitch protection is tested by the PEC.
The propeller brake system enables a safe use of the right engine to provide direct current and conditioning air on ground. This operation mode is called hotel mode. The propeller brake system is a hydromechanical system installed on the right engine reduction gearbox and prevents the propeller and power turbine from rotating when the system is activated. Hydraulic pressure for the propeller brake is supplied by the blue hydraulic system at a pressure of 3,000 psi. The propeller brake control and indicating system comprises the guarded prop brake toggle switch that ensures propeller brake engagement and disengagement. The green ready light, which indicates that all conditions for the propeller brake operation are met. The blue prop brake lights, one on the propeller brake panel and a second one on the memo panel, which are on when the propeller brake is engaged. And a red unlock warning light, which comes on when the propeller brake is not in the fully locked or released positions. Before activating the propeller brake, engagement or disengagement, the ready light must be illuminated. This light indicates that all the conditions necessary for propeller brake operation are met. For the propeller brake engagement, the following logic must be met. Propeller brake toggle switch selected on. Aircraft on ground. Condition lever number 2 on feather or fuel shutoff. Gust lock engaged. And blue hydraulic pressure available. Basically, the same logic applies to the propeller brake disengagement. The only difference is that the propeller brake toggle switch has to be selected off. Experience has shown that flight delays have sometimes been caused because the crew was not able to engage or disengage the propeller brake. The first example is when the gust lock is not properly set. Remember that it shall be pulled backward and then downwards in order to have the gust lock set at the correct position. The second example is when at least one of the weight-on-wheels sensors installed on the landing gear is not indicating that the aircraft is on ground. This may happen when the aircraft is loaded with the center of gravity too close to its aft limit, that is, tail-heavy, and by consequence the nose landing gear shock absorber becomes fully extended. When the engagement sequence is started, the blue system hydraulic pressure feeds the braking chamber inside the propeller brake. This operation takes some seconds, and while it is not completed, the red unlock light stays on. Once the propeller brake reaches the fully locked position, the blue prop brake lights come on. If after 15 seconds the propeller brake has not reached the fully locked position, the unlock light remains on and the following warnings will be activated. The master warning flashing light. The red prop brake light on the crew alerting panel, and the continuous repetitive chime. The propeller brake disengagement sequence causes hydraulic pressurization of the braking and releasing chambers. As for the engagement sequence, this action takes some seconds to be completed, and the unlock light stays on during the releasing while the propeller brake is in the intermediate position. When the propeller brake reaches its fully disengaged position, the red unlock light go off. If after 15 seconds the propeller brake releasing sequence is not completed, the unlock light stays on. And the following warnings will be activated. the master warning flashing light, the red prop brake light on the crew alerting panel, and the continuous repetitive chime. Note that loss of one of the engagement conditions will not prevent the propeller brake disengagement. Nevertheless, if the gust lock is released while the propeller brake is engaged, the red propeller brake light illuminates on the CAP, together with master warning and the continuous repetitive chime. In case a system failure is detected without any action on the propeller brake toggle switch, the CCAS will activate the following indications to the pilots: the master warning flashing light, the red prop brake light on the crew alerting panel, the red unlock light on the propeller brake panel, and the continuous repetitive chime.
Synchrophasing. The synchrophasing system provides propeller synchrophasing capability. Engine 1, left-hand side, is the synchrophasing master, and Engine 2, right-hand side, is the slave. Selection of synchrophasing is automatically performed by PEC2. When both propellers have stabilized at the selected propeller governing RPM, synchrophaser control is initiated even during takeoff. The master propeller incorporates an additional single-coil pulse generator to supply its propeller speed signal to the PEC2. PEC number 2 then sends a signal to its PVM to readjust the blade angle of the slave propeller. Speed control and synchrophasing accuracy supplied by the PEC limits the amount of bias on the slave propeller speed to plus or minus 6 RPM. If the RPM of either propeller differs from the selected governing RPM of the slave propeller by more than 6 RPM, synchrophaser control is deactivated.
There are 4 control modes: the fuel governing mode, the blade angle governing mode, the transition mode, and the hotel mode.
Fuel governing mode. This is the ground governing mode at low power. The EEC automatically increases the fuel flow to maintain the propeller speed at 70.8%. The condition lever, CL, is ineffective and is normally placed at auto. Note, this control mode is cancelled when the EEC is off, when the propeller is in feather position, or when the PEC is set to off. Transition mode. This is the mode between the fuel governing mode and the blade angle governing mode. It only applies on ground or in flight at low power and low speed.
The NP speed is comprised between 70.8% and 82% NP, or 100% NP depending on the power management selection.
Blade angle and speed controls. This is the normal in-flight governing mode. The PVM adjusts the propeller pitch according to the power setting in such a way as to maintain a constant propeller speed in P, whether the EEC is on or off.
This means the condition levers in auto position keep the NP required according to the power management selector position, 82% or 100%. And the power levers in the notch position maintain the maximum available torque for the given NP. The hotel mode is used only on ground and is only available on the right engine. In this mode, the propeller rotation is blocked by means of a propeller brake. Once the right engine is running, it can deliver DC electrical power and bleed air from the high-pressure compressor to both air conditioning system packs. The respective condition lever must be set to feather before engaging the propeller brake and shall be kept in this position during the utilization of the hotel mode.
The power lever controls the power of the gas generator, NH, since the fuel governing function is automatically cancelled when the condition lever is set to the feather position.
If the EEC is disabled, the maximum power available is lower, and by consequence, the air conditioning system performance is also lower.
Assuming that the engine is running with the power lever at ground idle and condition lever in the feather position, when the condition lever is moved from feather to auto, the fuel governing mode is activated. The propeller unfeathers and speed increases. Following unfeathering operation, the propeller blade angle reaches the low pitch blade angle. This is indicated by the low pitch light. After a while, the propeller reaches 70.8% NP. From then on, the EEC controls the engine fuel flow in order to maintain this propeller speed. This is called the fuel governing mode, and the AC wild generator becomes available. Note, the fuel governing mode is cancelled with EEC off or fault, or PEC off. Moving the power levers from ground idle slightly above flight idle causes the blade angle and by consequence the torque to increase. Close to flight idle position, the low pitch light extinguishes. Propeller speed is maintained at 70.8% because the fuel governing mode is still active. As the power levers are continuously pushed forward, the blade angle and the torque increase further. The propeller speed increases above 70.8% NP. This is called the transition mode. Passing 52 degrees of power lever angle, 100% NP is reached, assuming takeoff is selected on the power management selector. The PEC is now controlling the propeller speed in what is called blade angle and speed control mode. Moving the power lever towards the notch position, the NP is kept at 100% and the torque increases up to the maximum available takeoff torque. During approach, takeoff is selected, but the propeller speed is not 100% NP, rather 82% NP. This speed is used to minimize the noise during approach. As soon as the power lever is selected above 62 degrees of power lever angle, for example during a go-around, the propeller speed is increased from 82 to 100%. If the condition lever is selected to 100% override position, the logic described earlier is bypassed, and the PEC forces the propeller speed to be kept at 100%. During normal operation and no fault ID detected within the system, following touchdown, a ground flight logic resets 82% NP to 100% to allow the reverse operation. The overspeed governor will allow momentary propeller overspeed to reach full reverse operation. In any case, the overspeed is limited to 15 seconds.
The aircraft engines are fitted with an automatic takeoff power control system, ATPCS, that provides, in case of an engine failure during takeoff, an increase of 10% of the actual takeoff power on the remaining engine and an automatic feathering of the propeller on the failed engine. Both uptrim and auto-feathering functions are available for takeoff only. In flight, in case of a go-around, only the auto-feathering function of the ATPCS system is available. The ATPCS system allows a reduction of around 10% of the maximum certified takeoff power, thus increasing the power plant life without affecting the aircraft performance in case of an engine failure during the takeoff phase. The components of the system mounted on each engine are the Auto Feathering Unit, AFU, which is the main system element. It receives the torque signal coming directly from the engine and sends it to the cockpit torque indicator, needles only, FDAU, and MFC. The MFC is responsible for delivery control signals to the feather solenoid, to the electrical feathering pump, and to the operational EEC in case of an engine failure. This will ensure the correct auto-feathering and up-trim logic functions. The engine electronic control, which is responsible for enabling the power to increase from takeoff to reserve takeoff in case of an engine failure during the takeoff. The feather solenoid mounted on the propeller valve module, PVM, and electrical feathering pump located on the propeller gearbox. In the cockpit, there are the ATPCS push button to enable the flight crew to select the system on and off, a micro switch that senses the power lever's position, and a system test selector located on the center pedestal. To arm the ATPCS system on ground for up-trim and auto-feathering functions, the following conditions must be met. Power management selector set to takeoff. ATPCS push button on. Both power levers must be above 49 degrees of power lever angle, and both torques must be above 46%. The same conditions must be met to arm the ATPCS system in flight, but only the auto-feathering function will be available. If one of the conditions is no longer met, the system will be disarmed. In normal conditions, meaning without an engine failure, selecting the power management selector to CLB disarms the system. In case of an engine failure, and if an engine restart is performed, the flight crew must select the power management to MCT in order to disarm the ATPCS system, thus allowing the propeller to unfeather. The ATPCS green arm lights located above the engine instruments indicate that all ATPCS arming conditions are met. If one engine torque drops below 18%, the up-trim function is triggered and the engine bleed valve is closed on the operational engine. The flight crew shall observe the green up-trim light illuminated for the operative engine, and that the engine has the correct torque. 2.15 seconds after the engine failure is detected by the ATPCS system, the auto-feather is activated on the failed engine propeller. Once the ATPCS sequence is initiated, the up-trim is maintained on the remaining engine and the green ATPCS arm light extinguishes. Note that the ATPCS system is disarmed if at least one power lever is reduced below 49% of power lever angle within 2.15 seconds after one engine has failed. This time delay enables the flight crew to reject a takeoff run by pulling the power levers backwards up to full reverse position, thus avoiding having to feather the propeller. By doing so, the propeller blades will move up to the full reverse pitch, thereby increasing the drag and helping to stop the aircraft. If the up-trim function fails, the crew must manually set the reserve takeoff power by advancing the respective power lever until the torque indication matches the FDAU amber bug. Each engine is fitted with sensors and probes to control and monitor the engine operation. Two torque sensors mounted on the reduction gearbox sense the torque applied to the torque shaft that links the first and second stage gears inside the reduction gearbox. One of them sends a signal to the auto feathering unit, which supplies the analogic torque indicator pointer. The other torque sensor sends a signal to the EEC, which supplies the digital torque indicator. The propeller speed sensor is mounted on the top left side of the propeller reduction gearbox. To give the correct internal turbine temperature indication, 9 thermocouples are installed between the low-pressure turbine and the first stage power turbine. 2 high-pressure compressor speed sensors are installed at the right side of the rear air inlet case. Now that you know the location of the sensors, let's see the instruments available in the ATR cockpit. The torque indicators, which are located on the engine instrument panel, are powered from the DC emergency bus. The indicator dial is marked as TRQ%. And the scale on the indicator fixed dial is marked with major graduations in increments of 10% between 0 and 120%. A digital display on the indicator face gives an equivalent digital readout of torque. Note that a sequence of 3 zeros is displayed if the respective torque sensor has failed. If dashes are displayed, the EEC cannot control the HBV, which automatically closes. Finally, if the letters LAB are displayed, it indicates that a wrong engine electronic control is installed. The FDAU Amber target bug displays the maximum torque value computed by the FDAU for the actual power management position. The only exception is for the takeoff position, which will display the RTO torque. The white manual target bug, controlled by a knob located on the right bottom of the instrument, displays the manual selected torque target. The torque indicator range marks are a green sector from 0 to 100%, an amber sector from 100% to 106%, a red mark at 100%, a dashed red radial at 106.3% torque, and a red dot at 120%. By pressing the test button with power applied to the instrument causes the pointer to display 115% of torque with an equivalent reading on the digital display. A blue dot is available on the indication scale to easily identify the 115% position. The NP indicators are powered from the DC Essential bus. The indicator dial is marked NP%. And the scale on the indicator fixed dial is marked with major graduations in increments of 10% between 0 and 120%. A digital display on the indicator face gives an equivalent digital readout of NP. The NP indicator range marks are a green sector from 70.8% to 100%, an amber sector from 41.6% to 65%, a red mark at 100%, and a red dot at 120% NP. Pressing the test button with power applied to the instrument causes the pointer to display 115% of NP with an equivalent reading on the digital display. A blue dot is available on the indication scale to easily identify the 115% position. The internal turbine temperature indicators are powered from the DC Essential bus. The indicator range marks are a green sector from 300 to 765 degrees Celsius, an amber sector from 765 to 800 degrees Celsius, a white-red mark at 800 degrees Celsius, temperature limit in up-trim conditions, a red point at 840 degrees, temperature limit during 20 seconds, a red dot plus S at 950 degrees, temperature limit during 5 seconds for engine start. A red dot plus H at 715 degrees Celsius, temperature limit in hotel mode. And a red mark at 765 degrees Celsius, temperature limit during normal takeoff. An alert light illuminates amber and the CCAS is activated when internal turbine temperature is above 800 degrees Celsius or 715 degrees Celsius when in hotel mode. Pressing the test button with power applied to the instrument causes the pointer to display 1150 degrees Celsius with an equivalent reading on the digital display. A blue dot is provided on the indicator to identify the 1150 degrees Celsius location. The high-pressure compressor in H and the low-pressure compressor in L rotor speed indicators are powered from the DC essential bus. The indicator dial is marked NH%, and the scale on the indicator fixed dial is marked with major graduations in increments of 10% between 0 and 100%. A digital display on the indicator face gives an equivalent digital readout of NH only. As explained during the fuel system chapter, fuel is stored in 2 tanks, one in each wing. The fuel capacity of the ATR72 is 2,500 kilograms per tank, giving a total of 5,000 kilograms. Normally, the left engine is supplied from the left tank and the right engine is supplied from the right tank. Due to the location of the fuel tanks, fuel consumption will alter the aircraft's center of gravity during flight. During refueling, the center of gravity moves rearward. When the engines are running, and thus burning fuel, the center of gravity moves forward. The influence of the fuel consumption on the center of gravity shall also be considered when preparing the weight and balance sheet. Here you can see the influence of a 3,000 kilogram fuel uplift and a 2,000 kilogram trip fuel consumption during flight. The ATR-72 has 2 cargo compartments, one forward and one aft. Moreover, the forward cargo compartment is divided into the right forward compartment and left forward compartment. The aft compartment is divided into 2 sections, forward and aft. Depending on the number of passenger seats installed, the maximum load in each cargo compartment varies. In a 68-passenger configuration, for example, the following applies. The right forward compartment has a maximum capacity of 288 kilograms and 1.8 cubic meters. The left forward compartment has a maximum capacity of 448 kilograms and 2.8 cubic meters. The forward-aft compartment has a maximum capacity of 254 kilograms and 1.6 cubic meters. The aft section of the aft cargo compartment has a maximum capacity of 466 kilograms and 2.9 cubic meters. The holding system of each compartment is supported by masts, nets, and tie-down points. Note that if any element is damaged or inoperative, the affected cargo compartment maximum weight will be limited. Observe the following tables and check the limitations for each situation. Let's see the airplane floor loading limits. Click on the highlighted areas to learn more about them. The tail prop must be installed before loading or offloading the aircraft. This is to avoid a tail strike or possible damage to the aircraft. If for any reason it's not possible to install the tail prop, the following procedure must be followed. Maintain the forward cargo load at least equal or higher than the aft cargo load. Do not allow more than 10 passengers to stand in the rear aisle or in the rear passenger entrance area if the forward cargo load is not at least 200 kilograms higher than the rear cargo load. Ask the passengers in the forward part of the cabin to remain seated until the loading or offloading is completed. Also very important, it's prohibited to carry loose freight or baggage out of the specific area, and to load any freight or baggage that can damage or pass through the net. At the end of this section, you'll understand the physical basis of performance topics. Understand the general and ATR-specific terms and definitions. Be able to apply the relevant tables and graphs during all phases of flight, under normal and abnormal conditions. Have a good knowledge of the principles of flight planning and the application of the appropriate tables and graphs. Understand the specific requirements of special operations. Dispatch with malfunctions. During this chapter, we'll cover not only theoretical aspects, but also operational procedures and pilot actions. Note, the content of this chapter is based either on official ATR documentation and/or EASA regulations. Let's start this chapter with a review of some important definitions. Calibrated airspeed, CAS. This speed takes into consideration the difference between the total pressure and the static pressure. This difference is called dynamic pressure. The pitot tube is responsible for providing the total pressure, while the airplane's static probes are responsible for providing the static pressure. Indicated airspeed, IAS. The IAS is the speed indicated by the airspeed indicator. This speed would be ideally equal to the CAS. But due to various factors such as the aircraft angle of attack, flap selection, wind corrections, ground proximity, and so on, the IAS is slightly different than the CAS. This difference is called instrumental correction. The correction factor can be found in AFM section 6.01. True airspeed, TAS. This is the aircraft speed in the airflow and can be obtained by correcting the CAS for the air density and compressibility. Ground speed, GS. The ground speed is the TAS corrected for the wind component. Let's now review the meaning of the maximum speeds used for the ATR-72. Maximum Operating Limit Speed, VMO. The maximum operating limit speed is 250 knots. Flap Extended Speed, VFE. This speed is established in order not to exceed the maximum flap speed for the corresponding wing flap position and taking into account the engine power. The VFE for flaps 15 degrees is 185 knots, and for 30 degrees it is 150 knots. Landing Gear Operating Speed, VLO. The VLO is the maximum speed at which it's safe to extend or retract the landing gear. The VLO is 170 knots for lowering and 160 knots for retracting the landing gear. Landing Gear Extended Speed, VLE. The VLE is the maximum speed at which the aircraft can fly with the landing gear down and locked. The VLE is 185 knots. The maximum brake energy speed, VMBE, is the maximum demonstrated brake absorption capability speed. There's not a fixed value since it depends on the wind component. Airport elevation. The outside air temperature. And normal or icing conditions. For the ATR, there are tables giving the maximum takeoff weight and the respective takeoff speeds for various conditions in order to comply with the maximum brake energy speed. The maximum tire speed, VTYRE, is the maximum speed that can be reached without damaging the tire structure. For the ATR72, the V tire is 165 knots. Let's continue now with the meaning of the minimum speeds. First, the stall speed VS1G. All ATRs except the 42-300, 320 have been certified according to JAR 25, so it uses VS1G as a reference to the stall speed. VS1G corresponds to the maximum lift coefficient, just before the lift starts decreasing. This speed is typically 6% greater than the VS minimum. In October 2000, JAR 25 introduced the notion of reference stall speed, VSR, which is the same as VS1G. At this moment, the load factor is equal to 1. The VSR can be calculated for different aircraft weights and configurations. The minimum control speed on the ground, VMCG, is the speed at which, in case the critical engine fails, it's possible to maintain the aircraft control using only the primary aerodynamic controls. The critical engine is the left one. This speed allows the takeoff to be safely continued using normal piloting skills. The aircraft is certified to operate normally on runways with a width of at least 30 meters. In case a specific modification is incorporated into the aircraft, it's possible to operate on runways down to 14 meters wide. For the ATR, the VMCG increases in case of narrow runways. The minimum control speed in the air, VMCA, is the speed at which, in case the critical engine fails, it is possible to maintain control of the aircraft. You can maintain a straight flight and a bank angle of not more than 5 degrees. The calculation of this speed takes into consideration the outside air temperature and the airport pressure altitude. The minimum control speed during approach and landing, VMCL, is the speed during approach and landing with all engines operating, at which, in case the critical engine fails, it's possible to maintain control of the aircraft. You can maintain a straight flight and a bank angle of not more than 5 degrees. At this speed, the ATR has demonstrated the ability to roll from an initial condition of a steady straight flight through an angle of 20 degrees in the necessary direction to initiate a turn away from the inoperative engine in 5 seconds or less. The VMCL is defined for flaps 15 degrees and 30 degrees. Let's move on to the relevant speeds during the takeoff phase. First, let's look at the engine failure speed, VEF. This is the speed in which the critical engine is assumed to fail. The VEF is assumed by the aircraft manufacturer and cannot be lower than VMCG. The decision speed, V1, is the maximum speed at which the pilots can decide to reject the takeoff run in case the critical engine fails, and are able to stop the aircraft within the runway limits. The V1 is a variable speed, and the time considered between the critical engine failure and the pilot recognition is 1 second. At the rotation speed, VR, the pilot initiates the aircraft rotation at a rate of about 3 degrees per second in order to reach V2 no later than 35 feet above the takeoff surface. The VR shall be equal to or higher than V1, or equal to or higher than 1.05 VMCA, whichever is higher. At the liftoff speed, V-loft, the lift is higher than the aircraft weight and the aircraft becomes airborne. For the ATR, this is not a limiting speed. The takeoff climb speed, V2, must be reached at no later than a height of 35 feet above the takeoff surface in case the critical engine fails. V2 will ensure a minimum regulatory climb gradient of 2.4% after takeoff, taking into consideration the aircraft at the takeoff configuration and the landing gear fully retracted. The V2 minimum shall not be less than 1.13 VSR or 1.1 VMCA, whichever is higher. Minimum maneuver speed low bank, VMLB, and minimum maneuver speed high bank, VMHB, are ATR-specific speeds. Upon reaching the acceleration altitude, the aircraft has to reach speeds to allow safe maneuvering capabilities. VMLB limits the bank angle to 15 degrees, while VMHB limits the bank angle to 30 degrees. Those speeds are based on the stall speed for a given weight to provide sufficient merging against stall, and they vary for normal or icing conditions, flaps configuration, 15 or 30 degrees of bank angle, and for the flight phase in icing condition only, taking into account the ice accumulation on the wings during the flight. VMLB for flaps 0 degrees, VMLB 0, is the best climb gradient speed, while VMLB 0 plus 10 knots is the best rate of climb speed with both engines running. Continue with the meaning of the landing speeds used for the ATR. Reference speed, VREF. This is the demonstrated speed at which the aircraft is stabilized on the final approach in landing configuration. VREF is used for the determination of the aircraft's certified landing distances. For the ATR, the VREF is the VMHB for the given weight, or VMCL, whichever is higher. In case any system failure affects landing performance, the ATR operational documentation indicates the correction to the VREF in order to compensate for the failure. Approach speed, VAPP. Approach speed is used during the final approach segment with the aircraft in landing configuration. This is the reference speed, VREF, increased by the wind factor. The wind factor is the highest of 1/3 of the reported headwind component velocity, or the gust in full. The maximum applicable wind factor is 15 knots. Go-around speed, VGA. The speed to be used in case of performing a go-around procedure is the minimum maneuver speed high bank, VMHB, increased by 5 knots or 1.1 VMCA, whichever is higher. This lesson is all about power settings. You will learn about engine power ratings and limitations, which power setting tables are available, and how to use the tables.